So weird Lewis structures, these are pretty much ones that will not appear on the A-level, but it's, I believe, remiss of the A-level boards not to include some discussion of these. So triple bond is found in which of the following species? Well, C2H2 we've already done before, contains a triple bond because you've got bond between the carbon, bond between carbon and hydrogen. You're still left with that each carbon needs 2 bonds, so it takes it up to a triple. Nitrogen, N2, well, each nitrogen wants 3 bonds, so the only way that 2 nitrogens can get 3 bonds is to have 3 bonds with each other. Now, Cn-, it's a polyatomic ion, so we cannot use common sense. So the way I like to do it, carbon has got 4 valence electrons, nitrogen 5, the minus means 1, so we got a total of 10 valence electrons to put in here. Let's start off, carbon bonded to the nitrogen. Well, when you do that, you've still got 3 sets of lone pairs you'd have to draw on each of the carbon and nitrogen to take them up to common sense. That is a total of 14 dots. We only want 10. So let's throw in a double bond by erasing 2 of the lone pair dots and putting double bond. Now we've got 12 dots. So we have to go down to a triple bond for 10 dots. So structure of cyanide, each atom got a lone pair and then a triple bond between them. This, of course, is one that if you're trying to do it with dot and cross, you might have some little issues with it. I'm not quite sure, quite frankly, how you would do that with dot and cross, which could be why it's not included in the A-level spec. Anyway, which one has triple bond? All of them. 19, which species has the same electronic structure as ammonia? That's ammonia and H3. So we got an atom in the middle with lone pair of electrons bonded to 3 other atoms. What we see here, as we replace all of these by their formulas, and I'm just going to whiz that through because I know you all know those formulas, is we have an atom bonded to 3 other atoms. Okay, so you can see that all 3 of them are going to have the same connectivity, a central atom bonded to 1, 2, 3 other atoms. Okay, the question is, of course, not the connectivity, but the electronic structure. So the next stage is, let's count the number of electrons, of valence electrons, and I'll just whiz this through, assuming you can do this, but you can see the first 4 will have 24 valence electrons, and this last one has 26 valence electrons. So without going any further, this is the odd one out, but let's prove that SO32- is the correct answer. Okay, so we'll start off with SO3. Okay, you bond sulfur to each oxygen singly, and then you put in enough extra dots to make every atom happy. So the sulfur in this first structure, it's already got 6 dots with its 3 bonds, so that's a lone pair. Each oxygen only has 1 bond, so that's 2 dots, so therefore needs 6 more dots or 3 lone pairs around it. Now when we count up in this structure the number of dots, there's 26 dots, which means that this is a valid Lewis structure for SO32-, for sulfate, right, with their 26 valence electrons. And this is an atom, middle atom, bonded to 3 other atoms with a lone pair. So that looks pretty good, pretty close to the NH3, just in terms of the general electronic structure. But let's prove to ourselves that these others with 24 valence electrons are not. Because how do we now draw SO3 that has 24 valence electrons? There's the SO3 with 26 dots. So what we will have to do is we'll have to remove the lone pair from the sulfur and then a lone pair from each of these other oxygens. Well, when we do that, we can get this picture here. But of course, I could quite easily have removed the lone pair from the bottom oxygen or the right-hand oxygen. So we have resonance here. This is testing the expansion material. And so the actual structure of SO3 would be drawn like this. You've got the sulfur bonded to each oxygen. Each bond is identical as somewhere between 1 and 2. It's actually 1 1/3 bond, or 4/3 of a bond. So we draw that as a whole bond and then a partial bond. Now that's SO3 with 24 valence electrons. Well, BF3, CO32-, and NO3- would all be exactly the same. They would all be isostructural and isoelectronic because they've got the same connectivity, an atom bonded to 3 other atoms, and the same number of valence electrons to put in there. Thus, sulfate with a lone pair on the sulfur has the same electronic structure as ammonia that has a lone pair on the nitrogen. Tough question until you're really practiced at drawing these lower structures. And talking of practice, which of the following species central atom obey the octet rule? Well, SiF4, silicon with 4 fluorines, is going to obey common sense. Of course, that's the answer, because with most common sense, it obeys the octet rule. But let's just demonstrate it to each other. PF4 minus, okay? Well, there's P with 4 fluorines on it, okay? Add up the number of dots, there's only 32, but phosphorus has 5, 4 fluorines 28, a minus sign, another one, 5 plus 28 plus 1 is 34, as we say here, so we need another lone pair on the phosphorus. SeF4, you'd think sulfur in the middle, bonded to 4 fluorines, no problem, again that's 32 dots, we want 34, need a lone pair on the selenium. ClF4, we think Cl bonded to 4 fluorines, again that's 32 dots, we want 36 dots, so we have to put 2 more lone pairs on the chlorine, giving us 4 more dots. And finally, XeF4, again 32. When you just draw the single bonds like this, you want 36. So therefore, the xenon, again, 2 lone pairs. Okay, so which one obeys the octet rule? Well, as we saw right from the start, the only one that can follow common sense, SiF4. Which has most lone pairs on the central atom? Well, NH3 obeys common sense. IF3 has 28 valence electrons, so we'll put in the I 3 bonds, that would have given us 24 dots, so we need lone pair up to 28 dots. SeCl2, selenium like oxygen or sulfur 2 bonds, chlorine 1 bond each, so obeys common sense. ICl2, we draw it out straightforwardly, and it would only give us 20 dots when we put everything with 8 dots, so 22, we have to put yet another lone pair on the iodine. And IF4 minus, very similar to what we just drew in the last structure. IF4 gives us 32 dots, so we need 2 lone pairs on the iodine. So which has the most lone pairs on the central atom? The one that has 1, 2, 2, 3, 2, so that one. Finally, yet more, which of the following species incorrectly match a number of lone pairs on the central atom? Sulfate, you draw it out, and actually with all single bonds you get 32. If you remember, sulfate is one that there is a debate over. Is it all single bonds, or is it 2 double bonds and 2 single bonds, which then have resonance? Doesn't make any difference in terms of the lone pairs, which is of course one of the reasons there's debate, because there's no good easy experimental way to say, oh yes, there's lone pairs or not lone pairs. Nitrate, fairly easy. We've got this structure here, which of course has resonance, but in this case doesn't matter with the resonance because no lone pairs on the nitrogen, so that looks good. I'm sorry, so doesn't have 1 lone pair, it has no lone pairs, so that's wrong. XeF2 is just like I3 minus. You draw it straight out, xenon with 2 bonds would have 2 lone pairs. That would only be 20 dots. You need another lone pair for 22. SO2 drawn plenty of places for you, the sulfur with a lone pair on it, as stated here correctly. And IF4 minus, we drew it in the last 2 structures, iodine with 2 lone pairs on it to take it from 32 dots up to 36 valence electrons, so that looks good as well. So one that is incorrectly matched with a number of lone pairs was the nitrate, because nitrogen has none, not 1. Tough stuff the first time you see it. A lot of this not on your A level, but I think adds something to your understanding of structures and is certainly very useful for the further consideration, as we will do in the second part of molecular structures when you look at VSEPR, the actual shapes of these molecules and ions.